So, a very good evening, everyone. Welcome to the Gate Boosters series of IMS GATE Academy. My dear students, probably in the last session, we have learned concepts regarding degree of indeterminacy, static indeterminacy, and kinematic indeterminacy. Then we have continued with how to solve different types of trusses, right? So, trusses, talking about the trusses, we have tried to figure out how to solve the determinate trusses, correct? When we talk about the Gate Booster series, my dear students, I have already told you these series or these sessions are planned in a manner so that you may get the entire content in just a limited period of time, right? So here we are coming up with the second session of structural analysis. The basic concept for conducting this second session of structural analysis is to discuss the different methods through which the structures can be analyzed, and also we will going to see the influence line diagram and how to draw these influence line diagrams. So starting with the second session of structural analysis, so we were talking about different type of structures, right? And in the structural analysis, I have already told you that we will be talking about only skeletal structures. Skeletal structures are those structures whose only one dimension is predominating. It may be its length, it may be its height, or it may be its width. If I talk about a column, the height of the column is predominating. If I talk about a beam, the length of the beam is predominating. So we are talking about and analyzing these skeletal structures. Now, how to analyze these skeletal structures? We have different methods. So the next topic of discussion is different methods of structural analysis. From the very basics, we know that if we have less number of unknowns than the available equations to solve, then these unknowns can be determined very easily. If we have less number of unknowns, then the number of equations, to determine these unknowns, then these unknowns can be determined very easily, right? If we talk about structural analysis, we have two different types of unknowns. First one are the forces or reactions. And second one is our deformations. And talking about deformations, we can have transitional deformation or we can have rotational deformation, theta and delta, right? So in our entire structural analysis, we have two types of unknowns: forces and reactions or deformations. When we talk about the number of unknowns with respect to forces, we have defined one parameter which is known as degree of static indeterminacy. Through degree of static indeterminacy, we identify how many unknown forces are present in the system. For determining the number of unknowns with respect to deformations, we have again defined one parameter which is known as degree of kinematic indeterminacy. So this degree of kinematic indeterminacy, dk, tells us about the unknown deformations. It can be a transitional deformation or it can be a rotational deformation. So just for your point of view, if for a system I have less number of unknown forces, means my degree of static indeterminacy of the system will be less than the degree of kinematic indeterminacy. Will it be okay? Will it be okay from your side? If I have less number of unknown forces, then less number of equations will be required to determine these unknown forces. And if we know the unknown forces of any structure, we can easily determine the different types of deformation occurring due to these forces, correct? So for determining the unknown forces, we have a parameter which is known as degree of static indeterminacy. And for determining the unknown deformations or the number of unknown deformations, we have a parameter which is known as degree of kinematic indeterminacy. So depending upon these two degrees of static and kinematic indeterminacy, we define which method to be used to analyze the structure, right? Obviously, if we have less number of unknown forces, we will go with that method through which we can determine the forces. Or if we have less number of unknown deformations, we can obviously choose that method through which these deformations can be determined, and using these deformations, further the remaining forces can be analyzed, right? So depending upon these two parameters, we have defined the entire methods for analyzing the structural analysis as force method and the displacement method. As the name says, force method, right? For force method, if the total degree of static indeterminacy of the system is less than the kinematic indeterminacy, then this force method has to be used. For force method, we determine the unknown forces first. Then after determining these unknown forces, we determine the unknown deformations. Is this clear? So for force method, we determine the unknown forces, and using these unknown forces, we determine the unknown deformations, correct? Now how to choose when to use force method? Whenever the degree of static indeterminacy of the system is less than the degree of kinematic indeterminacy, we choose force method for analyzing the structure. So whenever our system has less degree of static indeterminacy than kinematic indeterminacy, we use force method. So for force method, forces are taken as unknown. They are also known as compatibility or flexibility methods. They are also known as compatibility or flexibility. 1 minute, just 1 minute. Okay, so force method are also known as compatibility or flexibility method. Force method are used when degree of static indeterminacy is less than the degree of kinematic indeterminacy, and displacement methods are used when your degree of kinematic indeterminacy is less than the degree of static indeterminacy. Degree of kinematic indeterminacy tells us about how many number of unknown deformations are present in the system. If the number of unknown deformations present in the system are less number of equations are utilized to determine these unknown deformations, and after determining these unknown deformations, we can determine the unknown reactions of the system or unknown forces of the system. So for displacement method, your dk has to be less than ds. In displacement method, the deformations are taken as unknowns. They are also known as equilibrium method or stiffness method, right? So this diversification, when to choose force method or displacement method, should be clear in your mind, that whenever your degree of static indeterminacy is less than the degree of kinematic indeterminacy, you will go with force method, and in the other case, you will go with the displacement method. Next, if I talk about different methods that are known as force method, it includes method of consistent deformation, strain energy theorem, flexibility matrix method, column analogy, and three moment method, right? All these are force method. Good evening sir, a very good evening. All these are known as the force method, correct? But my dear student, here you have to be very precise in reading about these methods. Structural analysis is a kind of wide subject. Huge variety of conventional question can be framed from structural analysis. From GATE point of view, only method of consistent deformation, strain energy theorem, and some question, not many, some question can be framed from flexibility matrix method. Only these three methods are usually asked for your GATE examination. Not many questions are asked from column analogy and three moment method, because the questions framed from these two methods are of conventional type. But in the GATE examination, the majority of questions are very easy, and they are the simple multiple choice type questions, correct? When we talk about the displacement method, we have slope deflection method, we have moment distribution method, again we have a stiffness matrix method, and then we have Canny's rotation method. Again, for GATE point of view, your slope deflection method and moment distribution method are two important methods. Still, if I talk more precisely about these two methods, again a conventional type of question can be framed using these two methods. So the question asked from these two methods are through their basic principle, correct? Not the entire question is asked regarding to solve these two methods with respect to any structure. Is this clear to everyone? Okay. So moving on with our first method for analyzing the structure. First, see this question. Out of the force method or displacement method, which method should be used to analyze this beam? Okay, quickly tell me the answer. In order to decide which method to be used? You need to calculate the ds in dk. ds is the degree of static indeterminacy. So quickly calculate the degree of static indeterminacy for this beam. So degree of static indeterminacy for this beam, is r minus, tell me 3 or 2, just see the loading condition. The loading condition is vertical. For vertical loading condition, only two equilibrium conditions are considered, right? Only two equilibrium equations are considered. So ds is r minus 2. Talking about the number of support reactions, so we have 1, 2 and 3 support reaction for this support. Just 1 minute. So very sorry students, some mishap happened right with the screen. Okay, so we will continue with this. I am talking about how to calculate the degree of static indeterminacy for this beam, for determining which method has to be used, either force method or displacement method. If I calculate the number of, so degree of static indeterminacy is r minus 2, where r is due to the vertical loading condition, correct? If I talk about the number of support reaction, so number of support reaction is 3 for this support, 2 for this support, 2 for this support, 1 for this support and again 2 for this support. We will not going to consider any horizontal reaction. We will only going to consider the vertical reaction and the moment, right? So for this support, we have 2 reaction. For this support, we have 1 vertical reaction, and again for this support, we have 2 reaction, right? So the total of 5 unknown reactions. So degree of static indeterminacy is 5 minus 2, which comes out to be 3, right? Next is the degree of kinematic indeterminacy dk is equals to 3j minus r. So the number of joints are 1, 2 and 3. So 3 joints are there. So 3 into 3 minus number of support reaction. So don't confuse yourself for calculating the number of support reaction when we talk about degree of kinematic indeterminacy. For calculating the degree of kinematic indeterminacy, all the support reactions are counted, right? So for calculating the degree of kinematic indeterminacy, the number of support reactions will be, for this support it will be 3, for middle support it will be 2, and for the last support, right hand side support, it will be again 3. So the total number of 3 plus 3, 6 and 2, 8 supports are there. So here the degree of kinematic indeterminacy is equal to 1, right? As we know that degree of static indeterminacy, so degree of static indeterminacy, ds, degree of static indeterminacy comes out to be 3, and the degree of kinematic indeterminacy comes out to be 1. So degree of kinematic indeterminacy comes out to be 1. You obviously dk is less than ds, hence your displacement method, are used for analyzing this beam, right? So this is how you need to decide which method to be used when we talk about the force method and the displacement method. Moving forward, next is when we analyze the any structure, we have certain assumptions, right? First assumption is structure should be homogeneous, isotropic and elastic. Talking about the homogeneity and isotropic structure, the properties in every direction should be same for any structure, right? If the property of the structure in every direction along its entire volume is same, then that type of structure is known as the homogeneous and isotropic structure. Obviously, we only analyze structure which are under elastic range. Means if loads are removed, there is no permanent deformations in our structure. If loads are removed, our structure can get back to their original shape and size. The second assumption is the structure should follow Hooke's law. Means it has to be within the proportionality limit, where the stress is directly proportional to strain. Only in our part of analysis as a BTech graduate, we will going to analyze structure for this, right? When the structure follows Hooke's law. The structure should have first order linear analysis. Now understand this. When we talk about first order analysis, it means that the deformations are not very observable, right? So the deformations are not major. We consider only minor deformations. Means if you consider any beam, if you just consider a beam like this, right? Consider a beam like this. If you apply any external load over the beam, there will be some deformations, and due to this deformations, you may observe the change in length of this beam, right? If you apply the external load like this, you may observe that the deformations in the beam may be something like this, correct? Now we know that if this is my original length L, obviously this original length L is less than my extended length L dash. This L dash has to be more than L, right? But in our analysis, what we do is, we do not differentiate between the extended length and the original length of our structural members, right? So this is known as the linear part, right? It is known as the first order analysis. Second is the linear analysis. When we talk about the linear analysis, the loads are directly proportional to the deformations. The loads are directly proportional to the deformations. The loads are directly proportional to the deformations. As you apply more load, you will observe more load in our you will observe more deformations in our structure. So when we talk about a first order linear analysis, for first order analysis, it means that the extended length of the member is equal to its original length. The second one is the linear analysis, where when you apply more load, you will going to observe more deformations. Moving on with this. Here we have a question. So we have the first method for analyzing the structure. It is more of a kind of remembering the standard results. If you remember the standard results, you can easily deal with these type of questions. And usually what we do is, the basic mistake that we do before attempting our GATE examination is, we do not focus in memorizing these standard results. Obviously, my dear students, everybody has that technical aptitude to derive these standard results, correct? You can do this practice at your home, but before going to examination, at least keep yourself that much prepared that once you know the entire derivation, you may also remember the end result of it, which will going to save your time for deriving that end result. You can directly utilize this end result for solving any structure. So when we talk about method of consistent deformation, it is totally based on the standard results. If you remember the standard results of deformations, you can very easily deal with the questions. Now take a question which says that a two-span continuous beam having two equal spans each of length L is subjected to a uniformly distributed load W per unit length. The beam has a constant flexural rigidity EI. The reaction at the middle support is, correct? The reaction at the middle support is. So let me draw a beam for you. So here we have a two-span continuous beam, each of length L. So here we have a two-span continuous beam, each of length L. So here we have a two-span continuous beam, each of length L. This beam has been applied with a UDL over its entire span. You need to calculate, this is my point A, this is my point B, and this is my point C. So the loading per unit length is W per unit length. So this is W kilonewton per meter. So this is my loading given. Now we need to calculate the support reaction RB. We need to calculate the support reaction RB, correct? We need to calculate the support reaction RB. For dealing this question using method of consistent deformation, first what you have to do is, whatever unknown force you need to determine, just release it from the system. That is, remove it from the system and take the deformation occurring due to loading. If you remove this RB, the kind of beam you will going to get will be something like this. So here we have a beam like this, loaded with UDL. The total length of the beam is 2L. The total length of the beam is 2L. The intensity of loading is W kilonewton per meter. The intensity of loading is W kilonewton per meter. Now, when this beam will going to deflect like this, you need to know the standard result of the maximum deflection that is occurring at that central point or at the point of RB. This is delta B due to this load W. Due to this load W, the central deflection that will be occurring will be equal to this delta B should be equal to, since it is downward, so 5 upon W into L raised to the power 4. So here we have total length as 2L raised to the power 4 divided by 384 EI, right? So here we have the standard result for calculating the deflection that will be occurring due to this uniformly distributed load at point B. So this is my standard result, right? So first what you did is, you have released this RB and you have calculated the deflection at point B due to unit load, right? As we know that due to this RB, there might not be any deflection at point B, correct? This point B does not contain any deflection. So what we will going to do is, we will going to apply the compatibility equation that delta at B will be equal to 0. So first we have released this RB force. Now what we will going to do is, we will going to only apply this RB force and we will going to calculate the deflection that will be occurring due to this RB. So again, I'll draw a beam like this. And this is my RB. And this is my RB. Quickly tell me the value of RB. Quickly tell me, quickly remember the standard result. Quickly just revise your standard result and tell me the value of RB. Quickly tell me the value of RB. So due to this RB, we will going to have the deflection of the beam in the upward direction like this. So this is my delta dash B due to RB. So delta dash B due to RB, delta dash B due to RB is RB into L, that is 2L raised to the power 3 divided upon 48 EI. Just check on this standard result and confirm me. Just check on this standard result, Prashant. Good evening. Check on this standard result and tell me. Okay, chalo. So this delta dash B is due to this RB, and here we have delta B due to this unit load, right? Now in this beam, as we have seen that due to this RB, the delta at B has to be 0. The delta at B, the total or net delta at B, the net delta at B has to be 0. This net delta at B is equal to this net delta at B, delta net at B is equals to delta B plus delta dash B. This has to be 0. Just substitute the value of delta B. So delta B is minus 5 upon 384 W into 2L raised to the power 4 upon EI. For this delta B, it is RB into 2L raised to the power 4, 2L raised to the power 3, it is 2L raised to the power 3 upon 48 EI. Quickly get me the answer of RB. Quickly get me the answer of RB. Please get me the answer of RB. Quickly get me the answer of RB. Just solve this equation and get me the answer of RB. I have a ready answer for you. So RB is equals to 5 WL by 4. So here, from here, RB is equals to 5 WL by 4. RB is equals to 5 WL by 4. So if I talk about method of consistent deformation, so method of consistent deformation, for method of consistent deformation, the steps to be used are, first one is release the redundant force, release the redundant force, release the redundant force. Second is calculate the deformations, calculate the deformations. calculate the deformations, and third one is apply the compatibility equations. Apply the compatibility equations. Apply the compatibility equations. So using these three steps, you can determine the unknown forces that are asked in the question. Again, this method is totally based when you exactly remember the standard results of deformations. When you 1 minute. When you exactly remember the standard results, that is how you can deal with the question using method of consistent deformation. Okay, moving on with this. Now the first method of solving any structure is known as method of consistent deformation. By remembering the exact or the standard result, you can solve the structure. Now talking about the next method, which is through the strain energy principle. My dear students, first of all, understand what do you understand by strain energy, right? When you apply load over any structure, some deformation may occur. It may be rotational deformation or it may be transitional deformation. The amount of energy stored due to these deformations are termed as the strain energy, correct? If I talk about the strain energy, it is the energy stored in a structure which is undergoing deformations, correct? When a structure undergoes deformations and when this external load is released, this structure will come back to its original shape and size. So while undergoing deformations, the amount of energy stored in the structure is known as the strain energy. The area under the load displacement curve is known as the strain energy, correct? So let me just draw one diagram for you. Quickly, let me draw a beam like this for you. It is a cantilever beam over which load is there, right? Load P is acting. Due to this load P, this beam will undergo some deformation delta. This beam will undergo some deformation delta, and whenever we talk about applying these loads are gradually applied. These are not suddenly applied load or impact load, right? They are gradually applied load. So when you gradually apply load, you will see the deformation in the beam. When you gradually apply load, you will going to see deformation in the beam. So this kind of deformation, if I plot a deformation on the x-axis and load on the y-axis, for a gradually applied load, this kind of deformations are seen, right? So when you increase the load, you will going to have more deformation. So area under this load deformation curve gives us the strain energy. So if I talk about the strain energy is stored due to load applied, so strain energy is area under the load deformation curve, that is half P into delta. So this is the strain energy stored when we talk about the gradually applied load. These are the gradually applied load. For a gradually applied load, the strain energy stored in the system is P into delta. When this load is suddenly applied, right? When this load is suddenly applied, the kind of load deformation curve you will going to see will be like this. This is the load deformation curve when the load is suddenly applied or the load is impact loading. So this is my P, this is my delta. So impact loading is, for impact loading, strain energy stored in the system is, area under this load displacement curve, which is nothing but P into delta, right? Which is P into delta. As you can clearly see here that the strain energy stored for the impact loading is more than the strain energy stored for the gradually applied load. Correct? So just keep these things in your mind, because a multiple select question can be framed or a statement can be framed using these two relations. For a gradually applied load, the strain energy stored is half P into delta. For a impact loading condition, the strain energy stored is P into delta. Always the deformations can be caused by the axial force, shear force and the bending moment, and last one is the twisting moment. So these are the different type of force which can cause the deformation. If you apply the axial load, you will see the axial deformation. If you apply the bending moment, you will going to see the bending action. If you apply the twisting moment, you will going to see the twisting action. And if you apply the shear force, you will going to see the shear action. Correct? Next is, okay. So the strain energy due to axial deformation is half P into delta. This delta can be written as PL upon AE. So the strain energy due to axial deformations comes out to be P square L upon 2 AE. So when we have analyzed these trusses, right? For these trusses, the forces present in the member are the axial forces. No bending moment and no shear stress is present in the trusses, correct? So when we talk about the strain energy present in the truss, it will only be due to the axial force, and the strain energy stored in every member is just summed up to calculate the total strain energy stored in such kind of frames, right? A pin jointed frame or a truss. For a pin jointed frame or a truss, the total strain energy stored will be due to the axial deformations, and it is the summation of the strain energy of the individual member, that is summation of P square L upon 2 AE, where P is the member force, L is the length of the member, A into E is the axial rigidity, right? Now, moving on with this, here we have a question which says that you need to calculate the strain energy for the system shown in the diagram. Just try and calculate the strain energy for the system. Please calculate the strain energy for this system which is shown in the diagram. You need to calculate the member's force first, and then you need to calculate the strain energy, correct? First calculate the member forces. You have member AC and BC only. At point C, an external load W is applied, right? The axial rigidity for this member BC is 2AE and length is L. And for this member AC, the axial rigidity is AE and the length is again L, right? For calculating the strain energy stored, first of all, we need to know the member forces AC and BC, right? You have n number of methods for solving, right? You can just calculate the support reaction and then go back to these members by taking or considering one joint, correct? We have one shortcut for this. Just try to see this. So here we have a structure like this. We have one member like this. We have one member like this. And over these two members, some external load W is acting like this, right? So this is W. This is my member force. Let me consider the tensile member force. This is my member AC. This is point C. And this is point B. Let me also consider the member force in CB as tensile. So this is FCA, and this is FCB. The angle, this angle is given us as 45 degree. This angle is 45 degree and this angle is also 45 degree, right? So what you have to do is you have to just apply one rule, that load and the opposite angle. So this angle is 90 degree. This angle is 90 degree. Opposite to this force, this entire angle is 45 plus 90. So this entire angle is 135 degree. This is 135 degree. Similarly, this angle is also 135 degree. This angle is also 135 degree corresponding to this force or member AC, right? So you have to just take the simple relation, that is force load W divided by the sine of the opposite angle. So opposite to this load W, we have 90 degree. So sine 90 degree will be equal to force in the member or force CA divided by sine of the angle opposite to this member. So opposite to this member we have angle of 135 degree. So sine 135 degree equal to FCB divided by sine 135 degree. Right. So just calculate this. You will going to have FCA equal to W into sine 135, that is 1 by root 2, divided by sine 90, which is 1. So FCA comes out to be W by root 2. FCA comes out to be W by root 2, right? And this is tensile in nature. Second, similarly, FCB is equals to W into 1 divided by root 2 by 1. So this is again W by root 2. And this is also tensile in nature, right? So we have both the member forces, that is force in the member CA is W by root 2 into T, and we have force in the member CB as W by root 2 into T. Correct, Prashant, it is Lamy's theorem. Okay, so using these Lamy's theorem, we can simply determine the member forces. Once we have the member forces, we can calculate the total strain energy of the medium. So the total strain energy of the medium is equals to FAC on plus FBC. Strain energy stored in the member AC and strain energy stored in the member BC, right? So strain energy stored in the member AC is equals to FAC square into L upon 2AE plus for UBC it is FBC square L upon 2AE, right? Here it is given as EI, it is AE. There is some printing mistake in this question. Okay, AE is only given. So for member BC, the value of AE is 2AE. So here we have to substitute 2AE. For member BC, here we have to substitute 2AE. 2 into 2AE. Just substitute the value of FAC and FBC. So FAC is W by root 2, taking the square, it will be W by 2. So WL by 4AE. It will be WL by 4AE. Similarly, FBC square is W by root 2, that will be W square here, W square. So this is W square L upon 4AE, and here it will be W square L divided by, so this is 2 and 8AE. Just take the LCM and get me the final value. So WL square by 4AE plus WL square by 8AE, this might come out to be 3WL square by 8AE. So this is my final total strain energy of the medium. This is my total strain energy of the medium, 3W square L by 8AE. 3W square L by 8AE. Okay. So this is my final or total strain energy which is stored in the structure which is given to us. So here we have a structure which is given to us. So for this structure, the total strain energy stored in this structure is equal to 3W square L divided by 8AE. So obviously you have got this. Any confusion in this? Any confusion in calculating the strain energy? When we talk about calculating the strain energy, just calculate the strain energy of the individual member and add the total strain energy for all the members, right? That will going to give you the total strain energy of the medium. Chalo, moving on. Next one is the Castigliano's theorem. Now Castigliano's theorem is used to determine the deformations. Using the Castigliano's theorem, first of all, the statement for Castigliano's theorem states that for a linear elastic structure, the partial derivative of strain energy with respect to the load will going to give us the displacement at the point of application of the load and in the direction of the load. Just to make it easy, what Castigliano's theorem does is, if you know the strain energy of the medium, if you know the strain energy for this beam, for suppose a load is applied W, right? And you are asked to calculate the displacement due to this load W. If you are asked to calculate this displacement due to this load W, what you will do is, you will just partially differentiate the total strain energy of the medium with respect to this load W, and you will directly going to get the deflection due to this load W, right? Obviously, this load is a point load, so it will going to give us this deflection of delta, correct? Similarly, if any moment is applied, it will going to rotate the member. Any moment will going to rotate the member. So the deformation occurring due to this rotation or this moment will be rotational deformation. And the value of this rotational deformation theta b can be simply calculated by partially differentiating this total strain energy of the medium, not with respect to W. So this, I'll just correct this expression. So this theta b, it is equal to del u by del m. If you just partially differentiate the strain energy with respect to the moment, you will going to get the rotational deformation at that particular point where your moment is applied, right? So Castigliano's theorem gives us the deformation either due to point load or due to any moment. Due to point load, we will going to get this delta. Due to this moment m, we will going to get the value of rotational deformation, that is theta. Okay, so moving on with this. Same question is there. Find the vertical deflection at point C. Find the vertical deflection at point C. Just now we have calculated the total strain energy for this medium, correct? Now using that strain energy, we have to simply partially differentiate that strain energy with respect to this load W to get the deflection of this point C. Is this clear? This is just to show you how we apply this Castigliano's theorem. For applying this Castigliano's theorem, we will going to write the total strain energy that we have just calculated. So in the previous question, the total strain energy of this medium was calculated as 3 W square L divided by 8 AE. This is the total strain energy that we have calculated for this structure. Okay, just quickly partially differentiate this U with respect to this load W and get me the value of deflection at point C, vertical deflection at point C. Get me the value of vertical deflection at point C. Quickly get me the value of vertical deflection at point C. One more thing. When we partially differentiate the total strain energy with respect to the load, if we are getting the positive result, it means that deformation is occurring in the direction of load applied, right? But if we get the negative result, it means the deformation that are occurring in the system is in the opposite direction. Is this clear to everyone? So here if we get the positive result of deflection, so just partially differentiate to get the central deflection of point C. So delta C is equals to del U by del W. So del U by del W, this del by del W of 3 W square L divided by 8 AE. Just quickly get me this value of central deflection at point C. Quickly get me this value. Del by del W of 3 W square L upon 8 AE. 3 WL by 4 AE. Correct. It is 3 WL by 4 AE. So delta C is 3 WL by 4 AE. So since we are getting the positive value, it means that the deflection is occurring in the direction of the load applied, right? So this is how you can calculate the deflection and the rotational deformation of any structure using Castigliano's theorem. Moving on with this. Next method for analyzing the structure is known as the unit load method, right? For unit load method, we will discuss three important cases. First one is for external loading case. For external loading case, the deformation delta is equals to summation of k into delta dash, and delta dash is the deformation coming due to external loading. When we will going to discuss the question, these things will be clear. Right now, you can just note down these formulas. So for unit load method, for external loading case, delta is equals to summation of k into delta dash, which is equal to summation of pkl by AE. This k is the member forces due to unit load. This k is the member forces due to unit load. This p is the member forces due to external loading. This p is member forces. Let me write p are member forces due to external loading. And K are the member forces due to unit load, right? Second is the temperature change case. For temperature change case, deformation delta is again equals to summation of K into delta dash. Here delta dash is the change in length due to the change in temperature. So delta dash is equals to L alpha delta T. Next one is the lack of fit. For lack of fit, the total deformation delta is equals to summation of K into delta dash. Again here delta dash is DLI, that is the lack of fit present in any member, and K is the different member forces due to unit load, right? Now taking this question, you can understand this unit load method. So in the question, a right triangular truss is made up of members having equal cross-sectional area of 1550 mm square and Young's modulus of 2 into 10 raised to the power 5. You need to calculate the horizontal deflection of the joint Q. You need to calculate the horizontal deflection of the joint Q. For solving this question, the first step is, step 1 is using unit load method. Step 1 is, or I will write in the next slide. Step 1 is calculate the member forces due to external loading. With respect to external loading, you will going to calculate the member forces which are known as P values. Right? So first calculate the member forces due to external loading. Come back to this question. Calculate the member forces, analyze this truss. First of all, tell me what are the support reaction. We have a simply support at the base. Just calculate the support reactions. Calculate the vertical reactions and the horizontal reaction at point R and the vertical reaction at point P. Quickly calculate and tell me. The reactions. First tell me the vertical reaction at point P. Calculate the vertical reaction at point P. Quickly calculate the vertical reaction at point P. Just 1 minute, this board is hanging. Okay, so here we have a question. First, calculate the support reactions at point P and R. So let me draw this diagram manually. So here we have a load of 135 kilonewton. Okay, so 6, 4.5 and 7.5. And this is 6 meter, 4.5 meter and 7.5 meter. This is my point P and this is my point Q. Correct? Sorry, P, R. This is Q. I have one vertical support reaction at P. This is my RP and this is my RR. And then I have one horizontal reaction HR, right? So just taking the moment about R to be 0, considering the moment about R to be 0, summation of moment about R to be 0, I have one clockwise moment of, anti-clockwise moment due to this 135 kilonewton load. So this is 135 into 6. So minus 135 into 6. Again, I have assumed this RP in the upward direction. So this is also clockwise. So this is RP into 4.5. So here this is also clockwise. So this is RP into 4.5. Calculate the value of RP and tell me. Please calculate and get me the value of RP. So this is 135. It is minus 135 into 6 divided by 4.5. Quickly get me the value of RP. 180 kilonewton downwards. Okay, so RP is 180 kilonewton minus 180 kilonewton means whatever direction we have assumed for RP, it is on the opposite side, right? So RP is acting in the downward direction. So the direction of RP, the corrected direction of RP is in downward direction like this. So this is my RP. This is my RP. So this is 180 kilonewton. Taking summation of vertical forces to be 0. So summation of vertical forces to be 0. I can get the value of RR as 180 kilonewton and it is in the upward direction. Similarly, taking the summation of horizontal forces 0, I can get the value of HR as 135 and the direction of HR is correct. So HR is 135 kilonewton. This is 135 kilonewton. So I have all the reaction forces. Now consider joint R, right? Consider joint R. For joint R, thus this horizontal load will be directly transferred to this member. This horizontal load will be directly transferred to this member. So force in the member PR is directly equal to 135 kilonewton because this angle is 90 degrees, right? Similarly, force in the member QR will be equal to the reaction force RR. So this is also compressive in nature, and the force in the member QR is equals to this reaction RR, which is 180 kilonewton. So we know two member forces, we know the member force in member QR and we know the member force in the member PR. This is again 135 kilonewton. This is 135 kilonewton. Okay. Now we only need to calculate this member force at point in the member PQ. For calculating this, consider joint P. You can calculate this angle theta. This angle theta is, sin theta is 6 by 7.5. Okay, so just take P sin theta will be equal to this 180 kilonewton. So consider the joint P. Consider joint P. For joint P, this is my joint P. For this joint P, I have one compressive force like this. This is my P into R. This is my P into Q. Sorry, this is P into Q. And this is my support reaction acting in the downward direction, right? Like this. So I'll just assume the direction of force to be tensile in member PQ. Take the vertical component, calculate this theta, and take the vertical component. So summation of Fy0 at point P will going to give us the value of the member force P into Q. So the value of member force P into Q is force PQ sin theta is equal to 180 degrees. Now sin theta is simply 6 by 7.5. So sin theta is 6 by 7.5. Get me the value of FPQ. Get me the value of FPQ. Quickly get me the value of FPQ. Quickly get me the value of FPQ and tell me. Quickly get me the value of FPQ and tell me. It comes out to be 225 kilonewton. And the nature of this force is again tensile. So FPQ is 225 kilonewton. So let me make one table for this. So here I'll write members, then forces, then I'll write strain energy. Sorry. So I have all the P values. I have all the P values for member PQ, then member QR, and then member P into R. So this PQ is 225 kilonewton and this is tensile in nature. This member QR contains, again, this force is compressive force, and this compressive force is, I guess, minus 180 kilonewton. And similarly for member PR, this is also compressive force, which is 135 kilonewton, right? Now what you have to do is, for this same structure, you have to just remove the external load. You have to just remove this external load, and you need to calculate the horizontal deflection at joint Q. For calculating this horizontal deflection at joint Q, first you have to remove this external load, and then you have to apply the unit load at this position and again calculate all the member forces. That will going to give you the K values. Right now, whatever member forces that we have calculated, these member forces are nothing but the P values. These are the P values. These are the P values. Now we would like to calculate the K values, and K values are nothing but the member forces due to unit load. These are the member forces due to unit load. Now for calculating this member forces, again consider this same truss. Again consider the same truss and apply a unit load because horizontal deflection of joint Q is asked to us. So this is Q, this is P and this is R. You need to apply one unit load at joint Q for calculating the horizontal deflection of joint Q, right? Now again we need to calculate. So we have one vertical reaction. We have one vertical reaction at P and we have one vertical reaction at R and one horizontal reaction at R, right? So I'll just quickly analyze this. Taking the moment about R to be 0, we can get the value of this vertical reaction at P. So taking the moment about R to be 0, the value of this P, this reaction at P, so this is my R dash P into this length is 4.5, 6 and 7.5. So this is 4.5, 6 and 7.5, right? So this Rp dash, I have assumed the direction in the downward direction for the reaction due to this unit load. This is my Rp dash. So this Rp dash into 4.5 is equal to this 1 into 6. 1 into 6. So quickly get me the value of Rp dash. Quickly get me the value of Rp dash. So Rp dash is 6 by 4.5. 6 by 4.5. So this is 4 by 3. So this is 4 by 3. And the nature is downwards. Nature is downward. Similarly, the value of the vertical reaction at R, this RR dash, this RR dash will be in upward direction, and by considering the summation of vertical forces to be 0, this RR dash is equal to 4 by 3 but in the upward direction. Similarly, by considering the summation of horizontal forces to be 0, this HR dash is equals to 1 kilonewton, 1. This HR dash is 1. So we have again calculated all the support reactions. After calculating all the support reactions, we need to calculate the member forces or the K values, right? For calculating the K values, again same method will be used. For this PR, this K value will be compressive in nature, and this is KPR. This is KPR, and it will be equal to this HR dash, which is nothing but 1. Similarly, this KQR is again compressive in nature, and the value of this KQR will be equal to this R dash R, and which is nothing but 4 by 3. Now for calculating this value of this KPQ, for calculating this KPQ, again you need to consider the equilibrium of joint P, and you need to calculate this value of KPQ. So I will directly calculate KPQ. KPQ is nothing but RR dash, that is RR dash is 4 by 3 divided by sine theta. So this KPQ dash is, please get me the value of KPQ dash, KPQ. Get me the value of this KPQ. Quickly get me the value of this KPQ. I have my answers ready with me. So this KPQ is 1.67. This is 1.67. Right, so this KPQ is 1.67. Now I have got all the P values and K values, right? My KPQ is 1.67, KPR is 1 and KQR is 4 by 3. So this, I'll just update this. KPQ is 1.67. KQR is 4 by 3, and this KPR is 1, right? Now I have got all the P values and K values. Now in order to calculate the strain energy U is summation of, deformation delta of Q in the horizontal direction is summation of K into P into L divided by A into E. Now in the question it is given that this AE is constant for all the members, but the length of the member is changing. So keep these things in mind while just substituting these values. So I have this KPQ multiplied by FPQ into length of PQ, that is 7.5, plus KQR into F of QR multiplied by 6, plus KPR into F of PR multiplied by 4.5, and this total is divided by A into E, that is given in the question. You can just substitute all these values and get the total deflection that will be occurring. Please get me the answer. KPR and KPR are negative. KPR, okay. So this KPR is compressive. Correct. Thank you for correcting me. So this KPR is negative. So this is also negative. Okay, this KPR is negative. This is negative, this one is negative because it is compressive, and this is also negative because it is compressive. Okay, thank you. So this is KPR and KQR. So this is KPR and KQR. So minus and minus will going to become positive. Okay, just get me the quick value by substituting all of these things. Anybody get me the answer for this? Deflection at H, horizontal deflection at H. You can just substitute all these values, and the final answer that you will going to get will be something like, so the horizontal deflection at Q is 15.69 mm. So this may be your final answer. You can get your final answer when you substitute all the value, right? So this is how you need to do when you deal with this type of question through unit load method. You have to calculate the P values, then you have to calculate the K values, then you have, for calculating the horizontal deflection or deflection in the direction of unit load, you have to take the summation of PKL by AE, and this will directly going to give you the value of deformation. Next, chalo. So this I have already told you how to deal with this. So you have to calculate the P values, then you have to calculate the K values, and then you have to use the summation formula, that is summation of PKL by AE. Next is, a chord member AB of a truss is subjected to the rise in temperature of 100 degrees Celsius. The horizontal movement of the truss joint B is, it is subjected to the rise in temperature of 100 degrees Celsius. Only member AB is subjected to the rise in temperature, right? Only member AB is subjected to the rise in temperature. If only member AB is subjected to the rise in temperature, what we do is, we need to calculate the horizontal movement of joint B. We need to calculate this horizontal movement of joint B, right? So what we will going to do is, we will going to apply a unit load, and applying unit load we will going to calculate all the K values. Then after getting the K values, what we will going to do is, so this horizontal movement of joint B is nothing but the summation of K values multiplied by the L into alpha into delta T, right? Now due to this unit load, you will going to have member forces for all the members, correct? Sir, are these questions will be asked? Obviously, these questions are asked in the examination. These are easy questions. We have consumed a lot of time for solving this, right? But when you try to solve in the examination, these questions hardly take any time. These questions hardly take any time when they are asked in the examination. You have to quickly calculate 3 member forces for calculating this K values. Sir, it is consuming time. Yeah, obviously this questions will going to consume time, but it totally depends on your practice. When you solve this question in your examination, this question can be solved hardly within 5 to 6 minutes. Hardly, right? Because in your examination, you will not going to do all the steps. Many of the steps will be directly done in your mind, right? For suppose calculating the support reaction, you will directly going to calculate it. You will not going to write each and every steps, right? So obviously, these are your examination questions only, right? These are not the questions which are framed from some other concept or what I should say, which you cannot expect in your examination. These are the previously asked question. We have only changed the data and we have provided this, correct? So all these questions are framed in such a way taken care the GATE examination. Okay, just try to solve this. Try to read the question and understand the question. Okay, for calculating the horizontal deflection, what you have to do is, you have to apply the unit load at point B and you can get the all the K values, right? And then you have to multiply it by the extended length, that is L into alpha into delta T. But this change is but the change in temperature is only happening for member AB. Only for member AB, this change is happening, not with the other members like AC, DC, CB and CD. No temperature change is happening, correct? So this L into alpha into delta T for the other members will be 0. For the other members will be 0. So when the question is framed with respect to the change in temperature, you only need to know the K value where the member is having the change in temperature. For in this question, a very good evening, sir. Good evening. For this question, the change in temperature is only with member AB. So only for member AB we need to have this K value, right? For rest of the members, already L into alpha into delta T will be 0. So there is no point for calculating the K values for the other members when the question is framed like this. Is this clear to everyone? So for dealing with this question, I'll just make this question quickly. So this is my question. So here I have a point load. This is, sorry, here I have a hinge support and the other side we have a roller support. So this is my hinge support and here I have a roller support. So what I have to do is, I have to just apply a unit load at this point Q. So this point is B, A, B, C and D. So this is A, this is B, this is C and this is D, right? Okay. If anyhow I can get the horizontal force at point A, that horizontal force at point A will be equal to the member force AB, right? This is a very simple question. Now this HA, this HA, this HA can be simply calculated by taking the summation of horizontal forces to be 0. So this HA plus 1 is equal to 0. So whatever direction of HA we have assumed, the HA will be acting in opposite direction. So this HA is minus 1. This HA is minus 1. This HA minus 1 means whatever direction of HA we have assumed, this HA will be acting in the opposite direction. So HA is acting in this direction. Consider this joint A. For this joint A, if you look into this joint A, this HA will be equal to the member force in AB. This HA will be equal to the member force AB, and this member force AB, that is nothing but the K value, this KAB is equal to 1 and it is of tensile nature. So directly we have calculated KAB. Now using this KAB, I can calculate the deflection at point B. So horizontal deflection at point B is KAB multiplied by L into alpha into delta T for member AB. For other members, this delta T is equal to 0. Hence, no point in calculating the value of K for the other members, right? Only the change in temperature is happening for the member AB. Therefore, the extension or the compression of the length will be taking place in member AB. So, this KAB is 1. Length of the member is, I guess, 4 meters. This is 4 meters. This is 4 meters. And alpha is 10 into 10 raised to power minus 6. So this is 4 meters. I'll just write it into mm. So this is 4000. This is 10 into 10 raised to power minus 6 multiplied by delta T, that is 100 degrees Celsius. Quickly get me the value of horizontal deflection at B. Just do the calculation and get me the value. So this answer you will get will be in mm. This will be in mm because the length we have substituted is in mm. This is the length that we have substituted is in mm. This is per degree Celsius multiplied by degree Celsius will be equal to 1, right? It cancels out. So 1, 2, 3, 4, 5, 6 and 10 raised to power 6 will going to cancel out, and the horizontal deflection at point B will be equal to 4 mm. So this is again a question asked in your examination. Just take care, whenever the question is framed from the change in temperature, you need to calculate the K values for only those members where the temperature difference is coming, right? You need not to calculate all the K values, okay? Moving on with this. Now we have a next question which says that for the truss shown below, the member PQ is short by 3 mm. The magnitude of the vertical displacement of joint R is. The magnitude of vertical displacement of joint R is. Whenever we use, good Prashant, it is 4 mm, correct answer. Whenever we use unit load method, you need to apply the unit load in the direction where the displacement is asked, right? So in the direction of displacement is asked, you need to apply the unit load. For this question, as the displacement asked is at joint R, so you need to apply the vertical load at joint R, vertical unit load at joint R, right? Again, whenever we have lack of fit, for lack of fit, the displacement delta is summation of K into lack of fit of the member into lack of fit of the member. DLI is the lack of fit of the member. For this question, only member PQ is having lack of fit, that is 3 mm. Whenever the member is short, this lack of fit is taken as negative, and whenever this member is too long, this lack of fit is taken as positive. Okay. So now again, If I talk about DLI for member PR, so this DLI for member PR, this member PR, so this DLI for member PR is 0, there is no lack of fit. Similarly, for member RQ, there is again no lack of fit. For member RQ, there is no lack of fit, right? So only lack of fit exists with, this member PQ, and the lack of fit with member PQ is equal to 3 minus 3 mm, minus 3 mm, minus 3 mm, right? Because the member is too short. Now, what I have to tell you is, you need to determine the vertical deflection at point R. So for calculating the vertical deflection at point R, you need to apply the unit load at point R. This is my unit load at point R. This is my unit load at point R. And by applying the unit load at point R, you need to calculate this K values. Is this clear? As we know that DLI for PR is 0, DLI for RQ is 0, so no point in calculating the K values for these two members. What we want is, we only want the K value for this member PQ. We want the K value for this member PQ. This can be calculated very easily. Now understand this. How to easily calculate and reducing our step, this question can be done in just a fraction of seconds. So understand this. This is a symmetrical structure. This unit load is symmetrically divided into half and half on the either supports. It is symmetrically divided into half and half on the either support, right? Talking about the horizontal forces, there are no horizontal forces. There are no horizontal forces. Please tell me, are there any horizontal forces? Are there any horizontal forces? Since there are no horizontal forces, just take the summation of horizontal forces to be 0. You will find that the horizontal reaction at point P is 0. Horizontal reaction at point P is 0. Okay. Now calculate the member forces for this member PR to get the member force for this member PQ. Consider this joint P. Consider joint P. Consider joint P. So this, we have a joint P. Through this joint P, this is my first member. This is my support reaction, that is 1 by 2, which is acting. Now this is my another member, and this is my joint P. For this joint P, this is my this is Q and this is R. So this is Q and this is R. This angle we know that this angle theta, for this sine theta, we are given with the data as sine theta is equals to 3 by 4. We are given with the data as sine theta is equals to 3 by 4. The member length is, this half length is 4 meter and this height is 3 meter. It is given in the question. Now, take the summation of vertical forces to be 0. Taking the summation of vertical forces to be 0, summation of vertical forces to be 0. So we have this KPR, this KPR into sine theta is equal to this 1 by 2 plus 1 by is equal to this 1 by 2. It is equal to this 1 by 2. I have assumed the direction of this KPR as compressive, right? Because this compressive force will going to balance this reaction at point P, right? So this KPR is sine theta is 3 by 4. So into 3 by 4. So this is 1 by 2. So it comes out to be 2 by 3. So this KPQ, sorry, this is KPR. So this is K into P into R. So this KPR is 2 by 3. This KPR is 2 by 3, right? This KPR is 2 by 3 and the nature of this KPR is compressive. The nature of this KPR is compressive, that is minus. Okay. Next, this KPR cos theta is equal to KPQ. So let me just assume the direction of PQ to be tensile. I have assumed the direction of PQ to be tensile. So this KPQ cos theta, KP summation of horizontal forces to be 0. So this KPR cos theta is equal to KPQ. So this KPR cos theta is nothing but 2 by 3. This is 2 by 3. This is 2 by 3. Wait, I have made a mistake. This sin theta is 3 by 5, not 3 by 4. This is 3 by 5. Again, this is 3 by 5. This is 3 by 5. So this is 1 by 2. So this is 5 by 6. This is 5 by 6. And it is compressive in nature. So this is 4 by 5 is equals to KPQ. Five by 6. So this KPQ is 5 and 5 cancels out. It is 2 by 3. So this KPQ is 2 by 3. We get the value of KPQ and we know the value of DLI of PQ. So DLI of PQ is minus 3 mm. Minus 3 mm. So this delta vertical of joint R is KPQ multiplied by DLI of PQ. So KPQ is 2 by 3. It is 2 by 3 multiplied by minus 3. So this comes out to be minus 2 mm. Minus 2 mm. This minus 2 mm means that we have assumed that the upper that this point R will going to go downwards. But the answer that we are getting is due to this lack of fit of 3 mm, that is the member PQ is short by 3 mm. So this joint R goes up by 2 mm. This joint R goes up by 2 mm. Okay, so whenever you get a minus sign, the direction in which you have applied the unit load, the deflection will occur in the opposite direction. Okay, so here we have got the answer as minus 2 mm. It means we have applied load in the downward direction, but the direction of displacement will be in upward direction, opposite to the direction where we have applied the load. Is this clear? Is this clear to everyone? Is this question clear? Please tell me yes or no. Is this question clear to you? Okay, chalo. Moving on with this. Next, we have standard results for strain energy. As I've already told you that strain energy will always going to store in a structure whenever a structure undergoes deformation. If a structure undergoes deformation due to bending, the strain energy stored is integration of mx square upon 2vi into dx. Similarly, if some shear is happening or the shear force is acting over any structure, the strain energy stored is the strain energy stored is integration of Vx square upon 2Ag into dx, right? For strain energy stored due to torsion, it is equal to Tx square upon 2Gj into dx, right? As per Castigliano's theorem, we know that the deformation delta can be calculated by partially differentiating the strain energy with respect to the load in the direction of which we want to have the displacement, correct? So I have just differentiated this strain energy. We know that this strain energy U is equals to integration of mx square dx, mx square upon 2ei into dx. When you differentiate this expression with respect to load W, you will get expression like this. It will be equal to integration of mx del mx upon del W into dx upon ei. This is again one of the important relation for calculating the deflection for any joint or any point, okay? So for calculating the deflection, this expression again can be used. This is again an important expression, okay? Calculate the strain energy. Calculate the ratio of the strain energy. The question says that the ratio of the strain energy of a cantilever subjected to a point load of W at free end to the total UDL of same W over the entire span, okay? Now, this kind of derivation we usually do at our home or during our conventional examination, not for GATE examination. For GATE examination, be prepared. Go prepared in your examination. Try to have something already read, right? We need not to derive everything directly in the examination. We can have some pre-read things, and using that pre-read things, we can quickly get the answer. It will going to save our time in the examination. In order to deal such kind of question, you can take help of the standard results. So for standard results of strain energy, for a cantilever beam, if a point load is acting at its free end, so if I draw a cantilever beam like this, and if I apply a point load W at its free end, right? The total amount of strain energy stored will be equal to W square L cube upon 6 EI. Due to this point load, this cantilever will undergo deformation like this, and it will going to have deflection of delta. So the total amount of strain energy stored will be equal to W square L cube upon 6 EI. Similarly, if a moment is applied at the end of the cantilever, if for any cantilever, moment is applied, then the total amount of strain energy stored will be equal to m square L upon 2 EI. Then for the strain energy stored due to UDL, it is equal to W square L raised to power 5 upon 48 EI, and for cantilever, UDL will be spread along the entire span, okay? So for this question, you need to calculate the ratio of the strain energy. For a cantilever subjected to a point load, okay? So strain energy subjected to a point load, it is equal to W square L cube upon 6 EI. It is equal to W square L cube upon 6 EI. Right? So this is the strain energy due to point load. Next is the strain energy due to total UDL of same W. So same W means, this total UDL means this intensity of loading multiplied by the length. This will be the total value of loading applied over the cantilever with UDL, right? So if I draw a cantilever like this, so if small w is my intensity of loading, this total W is W into L. So this is directly given in the question. You are not given with the small w. This W, total W is given as W into L. But we know the expression of strain energy for this cantilever for this load intensity small w. For this load intensity small w, this strain energy is equals to W square L raised to power 5 upon 40 EI. So this strain energy is W square L raised to power 5 upon 40 EI. But this is our small w. So the small w into L will be equal to capital W. So just replace this. You will have this W L raised to power 4 upon 40 EI. Take the ratio of these two strain energies to get your final answer. Take the ratio of, this is the strain energy due to UDL. This is the strain energy due to UDL. So when you take the ratio of the strain energy, so this is W square L cube. Okay. So this is W cube, sorry, this is not square, this is W cube L raised to power 5 upon 48 upon 40 EI. This is W, no, this is W raised to power 4. I get some printing mistake is there for this question, okay. Some printing mistake occurs. So you can calculate using these standard results. Okay, moving on with this. Next, we are given with the frame shown below, which is subjected to a vertical point load W at the free end, and you need to calculate the vertical deflection at point C, right? For calculating the vertical deflection at point C, this vertical deflection, since this load is acting in the direction of deflection, so this vertical deflection at point C is equals to the partial derivative of total strain energy of the system divided by with respect to its load W. With respect to its load W. Calculate the total strain energy of the system and take the partial derivative with respect to the load W. So here is the question is there. So using the standard results, you can just deal with this question by taking the using the standard result. What you have to do is take the member BC. For this member BC, take the member BC. So this is B, this is C, and load W is acting like this, right? So this is strain energy in the member BC. Strain energy in the member BC is W square L cube upon 6 EI. W square L cube upon 6 EI. Since this is a rigid joint, this can be considered as a fixed support, right? This is a rigid joint, hence considered as a fixed support. When you consider the member AB, for member AB, this is my member AB. Over this member AB, you will find a moment of W into L. This is a moment of W into L acting over this member AB. This is my member AB. Just now you have seen the relation for calculating the strain energy, which is m square L upon 2 EI. So here the moment is WL. So strain energy of member AB is m square L upon 2 EI. Substitute the value of m as WL. So you will have strain energy AB as W square L cube upon 2 EI. W square L cube upon 2 EI. You have the strain energy for the member BC. You have the strain energy for the member AB. Just add these two strain energies to get the total strain energy of the system. So the total strain energy of the system is UAB plus UBC. So this is UAB plus UBC. So UAB is W square L cube upon 2 EI. So U is W square L cube upon 2 EI plus UBC is W square L cube upon 6 EI. This is W square L cube upon 6 EI. Just add these two, you will get the total strain energy as, this is 1 by 2. So 1 plus 1 by 3, it will be 4 by 3. So this will be 2 by 3. So this will be 2 by 3 times of W square L cube upon EI. W square L cube upon EI, this is the total strain energy. For calculating the horizontal deflection at point C, so the horizontal deflection, vertical deflection at point C, you have to simply partially derive this strain energy with respect to this load. So the partial derivative of the strain energy with respect to this load is del by del W of 2 by 3 times of W square L cube upon EI. So this comes out to be, this will be 4 L cube upon 3 EI. So this will be, so this delta vertical of point C, delta vertical of point C is 4 W L cube upon 3 EI. 4 W L cube upon 3 EI. This is the total delta vertical of point C. This is how you need to deal with this type of questions, correct? Whenever you are given with a structure, you need to calculate the total strain energy, and using that total strain energy, you can very well calculate the vertical deflection in the direction of load. Just take this thing in mind, whatever, by whichever load you are taking partial derivative, only in the direction of the load you will going to get the deflection in the members. Is this clear? Okay, chalo. Moving on with this, we have one more question which says that a uniform beam EI constant PQ in the form of quarter circle of radius r is fixed at end P and free at end Q, where load W is applied. The vertical downward displacement delta Q at the loaded point Q is given by delta Q is equals to beta into W r cube upon 3 EI, where r is the radius of the quarter circle. Find the value of beta corrected to 4 decimal places. Just try this question. Try this question for once. Try this question. I have a bad throat today. Sorry for inconvenience. A uniform beam EI. Okay. So let me draw the beam. So the beam is like this. The beam is in the form of quarter circle. This is my point P and this is my point Q. At point Q, the vertical load W is acting. This is my load W and this is Q. This is P. Right, and this is the radius of the circle. You know that if you need to calculate the vertical deflection of joint Q, so the vertical deflection of joint Q is equals to the partial derivative of the total strain energy with respect to this load W. This will going to give you the vertical displacement of this point Q, right? in order to calculate the strain energy, as this strain energy is integration of mx square upon 2ei into dx, right? So this is the expression for calculating the total strain energy. As for different locations, you will going to have different value of mx. Therefore, the total strain energy for this curved beam has to be integrated from this point to this point, right? Now, in order to initiate the integration, this dx, this dx, this dx can be written as, this dx can be written as, this is my dx, this is my dx, this angle is d theta, this is d theta, this is my d theta. So this dx can be written as r into d theta. This dx can be written as r into d theta, and this point at this point, the moment at this point at any distance x, just 1 minute, at any distance x, the moment can be calculated, right? So just substitute the value of dx. So we have integration of mx square upon 2ei into r into d theta, right? Just get me the value of this mx, get me the value of mx at any section x. So at this section x, right, at this section x, due to this vertical reaction, there will be this mx. So this vertical reaction will be equal to W. There will be no horizontal reaction because summation of horizontal forces to be 0. So there will be no horizontal reaction because there is no horizontal force acting in the system. So we have only this vertical reaction, and this W into x will be by mx at any section xx from my point P. So this will be equal to integration of W into x divided by, so W into x the whole square into 2ei into r into d theta. I've just 1 minute. So this is okay. Okay. I've just made one more little mistake. So this is my x, right? This is my x. At section xx, my moment will be W into x, and this is the reaction at P, and this is equal to W, right? So this x is equals to r, and this is my theta, So this r into cos theta will be equal to my x. This r into cos theta will be equal to my x. This r into cos theta will be equal to my x. So r cos theta will be equal to my x. Just substitute the value of, so u we have integration of W square upon 2ei. So this is W square upon 2ei into x square into r into d theta. Okay, so this x square can be written as r cos theta. So this comes out to be integration of w square upon 2ei into r square cos square theta into r into d theta. Okay, am I making a mistake? Okay, no, chalo. So this is integration of w square upon 2ei into r cube into cos square theta into d theta. Okay, quickly get me the value of cos square theta. Quickly get me the value of cos square theta. I've made a mistake here. This is not cos theta. This is r into sin theta. So this distance is, अरे भाई, this is my r and this is my section xx. So this distance x is r sin theta. This is r sin theta. This is r sin theta. So this distance is my r sin theta. So this is r sin theta is equals to x. So this is sin square theta, r square sin square theta. So this is again sin square theta into d theta. Just correct this. Sir, when will we consider negative moment? In this question, whenever your moment is hogging moment, that moment is considered as a negative moment, right? Also, whenever your moment is an anti-clockwise moment, right? In that case, also you consider hogging moment, negative moment, right? Now, this sin square theta can be written as, this is integration of w square upon 2ei into r cube. This sin square theta can be written as 1 minus cos 2 theta by 2 into d theta. Just integrate this expression and tell me the value of beta. Just integrate this expression and tell me the value of the amount of beta that is coming. So this is, so u is integration of w square r cube upon 2ei one by 2 minus cos 2 theta by 2 into d theta. So this theta integrates from 0 to pi by 2. This theta is integrating from 0 to pi by 2. So this is pi by 2. So this is w square r cube upon 2ei into, this is pi by 2 only, and this minus cos 2 theta is sin 2 theta by 2. So this is integration of cos 2 theta is minus sin 2 theta by 2. So it is sin 2 theta by 2. So this is minus minus sine 2 theta by 2, and this is 4, and this is from 0 to pi by 2. So this is w square r cube upon 2 ei into pi by 2 minus sine 2 theta. So sine theta is sine pi is 0 and sine 0 is also 0. So this comes out to be 0. Just cross check it. This is 0 or not. Just cross check and tell me this is 0 or not. So here you will have the final answer. U is equals to w square r cube upon, so this is, sorry, this is pi by 4. This is pi by 4. So this is also pi by 4. So w square r cube upon 2 ei into pi by 4. In order to calculate the vertical deflection of point Q, just differentiate it with W. So del U by del W will be equal to the vertical deflection of point Q. This will be equal to W del by del W of W square R cube upon 2 EI into pi by 4. So when you differentiate it, you will going to have pi by 4 into WR cube upon EI. So when you compare the expression, this value is asked in the question. So this is the value of beta which is asked in your question, right? So this is the value of beta which is asked in the question. Sir, iteration limits. What are the iteration limits? Okay. So in the examination, you might not get a question where n number of iterations are required. Even for moment distribution methods, the kind of question that are framed can be solved in a single step of iteration, right? You need not to even go for the second cycle. Only one cycle of iteration is sufficient for solving a question for moment distribution method as well. So this is how you can deal with this question. Okay. Next is, we have Maxwell's Bette's theorem, which says that a beam AB is subjected to a load of 10 kilonewton at C. The deflection at D is 4 mm. When the load of 10 kilonewton is applied at C, the deflection at D is 4 mm. If the load of 4 kilonewton is placed at D, what should be the deflection at C? Just deal with this question, calculate this question and tell me. Okay. So we have these Maxwell's Bette's theorem. According to Maxwell's Bette's theorem, the virtual work done by virtual work done by P system of forces is equal to the virtual work done by Q system of forces. For suppose For suppose, let me take an example. Here you have a beam like this. For this beam, if you apply a load at point P, right? If you apply a load at point P, and this is my point Q, right? This beam will undergo some deformation like this. This beam will undergo deformation like this. So the deformation under point Q, this deformation under point Q, this deformation under point Q, this is delta Q dash, right? Next is, again, if I take a same beam and apply load at point Q, I have taken the same beam, and for this beam, I apply a load at point Q, right? If I apply a load at point Q, this is my point Q, this is my point Q, so this is my point P, this is my point P. Due to this load Q, this beam will again undergo some deformation like this. Due to this load Q, there will be some deflection at this point P, and this is delta P dash, right? This deflection at point Q is not caused by the load at Q. It is caused by the load at P, right? So this P is doing the, load at P. Similarly, for this beam, the load at Q is causing the deformation at P. So the virtual work done by P is P into delta P dash. Virtual work done by P is P into delta P dash. Similarly, this is equal to the virtual work done by load Q. This virtual work done by load Q is Q into delta Q dash. This Q into delta Q dash. This Q into delta Q dash. This is the Maxwell's Betti's theorem. This is the Maxwell's Betti's theorem. Similarly, we apply this theorem of virtual work for this question. In this question, what is given? It is given that due to a load of 10 kilonewton at point C, the deflection occurring at D is, so this is my delta D dash. Delta D dash is given to as 4 mm. This is given to us as 4 mm. In the question, it is asked that if the load of 5 kilonewton is applied. So let me draw another beam. So for this beam, if a load of 5 kilonewton is applied at D, this is 5 kilonewton load. If it is applied at D, what has to be the deflection at C? This deflection at C we need to calculate. This delta C dash we need to calculate. So according to Maxwell's Betti's theorem, we know that this load of 10 kilonewton, so the virtual work done by this load of 10 kilonewton will be equal to the virtual work done by this load of 5 kilonewton. So the virtual work done by this load 10 kilonewton is 10 into delta C dash is equal to 5 into 4 mm. This is 5 into 4 mm. So this delta C dash is 2 mm. So using these simple concepts of Maxwell's Betti's theorem, we can easily calculate the deflection at point, right? So using two force system and equating the virtual work done by the two force system, we can calculate the deflection under the load, right? Next, okay, next is, so this is how we have finished the force method of analyzing any structure. Next is the moment distribution method. Now we will going to see the displacement method for analyzing any structure. So for analyzing any structure, we have the another concept of moment distribution method. For moment distribution method, the questions are not framed from the iteration part, right? where we form a table and we go for n number of iterations. Obviously, it is an iterative method, but the questions are formed from the basic concepts of moment distribution method, and n number of questions can be framed from it, right? So starting with moment distribution method, it is an iterative method. So first is the absolute stiffness of the member. From the absolute stiffness of the member, we mean that stiffness is basically the force per unit deformation. Or you can understand that stiffness, from stiffness we mean that if we want to deform any member, for unit deformation, how much amount of force we need to apply, right? So any kind of stiffness is directly related with unit deformation. It is the total amount of force required to uniformly, or I should say to deform a body by unit, right? Second is the rotational stiffness. If I talk about rotational stiffness, I am talking about the rotational movement, right? I am talking about the rotational deformation. For doing this rotational deformation, I need to apply moment. So from rotational stiffness, what I mean is the amount of moment required for unit rotation. So rotational stiffness means it is the amount of moment required for unit rotation, which is given by m by theta. Next is when your far end is fixed. When your far end is fixed, right? When your far end is fixed. Point where you apply the moment is your near end. So here, this is my near end, this is my near end, and that one is my far end. So for unit rotation, for having a unit rotation, if by applying moment theta, if by applying moment m, I got a rotation of theta, then my stiffness, when the far end is fixed, the stiffness of this joint is given by 4 EI by L. Stiffness of this is given by 4 EI by L. Similarly, when my far end is hinged, the stiffness is given by 3 EI by L, and when my far end is, when the far end of the member is free, there will be no resistance against the deformation due to the moment applied. Hence, my stiffness will be 0. Second is the stiffness of a joint. It is the sum of the stiffness of all the members meeting at a joint, right? So let me just frame a question like this. If you have a joint like this, right? If you have a joint like this, where this is your fixed end, this is your hinged end, this is your hinged end, and this is your free end, and they are meeting at this joint O. So this is my point A, this is my point B, and this is my point C. If I need to know about the stiffness of member OA, so stiffness of member OA, KOA, is equals to 4 EI by L. It is equal to 4 EI by L, where L is the length of the member and EI is the flexural rigidity of the member. Similarly, the stiffness of the member OB, is equals to 3 EI by L. It is equal to 3 EI by L. And if my far end is free, the stiffness of the member OC, KOC, is equal to 0. KOC is equal to 0 when our far end is fixed. Now, if I want to know about the total stiffness of the joint, so the total stiffness of the joint, O is the summation of the stiffness of all the members meeting at the joint. It is the summation of the stiffness of all the members meeting at a joint. It is the summation of all the members. It is the summation of the stiffness of all the members meeting at a joint. So if I want to know about the stiffness of the joint O, so stiffness of the joint O is equal to stiffness of the member OA plus stiffness of the member OB plus stiffness of the member OC. So stiffness of the member OA is equals to 4 EI by L. It is equal to 4 EI by L. stiffness of the member OB is equals to 3 EI by L. It is 3 EI by L. And for OC it is 0. So the total stiffness of the member comes out to be 7 EI by L. It comes out to be 7 EI by L if the length and the flexural rigidity of all the members are same. L and EI are same for all the members. If L and EI are same for all the members. So this is how you calculate the total stiffness of the joint. This is how you calculate the total stiffness of a joint. This is how you calculate the total stiffness of a joint. Okay, moving on with this. So the stiffness of the joint is the sum of the stiffness of all the members meeting at a joint. Next is the relative stiffness. The relative stiffness of a member, it is the ratio of the moment of inertia and the length of the member. When the far end is fixed, the relative stiffness is I by L, and when the far end is hinged, it is equal to 3I by 4L. Okay, so just keep all these things in your mind in order to solve the question very quickly, because from moment distribution method, n number of questions can be formed from these basic definitions. And when you see the previous year GATE questions, you will find that the majority of the questions are framed from these basic concepts of moment distribution method. Is this clear to everyone? Any doubt till now? Any doubt till now? Any doubt till now? Say yes or no if you have any doubt. Okay, chalo. Moving on with this. So the relative stiffness when the far end is fixed is I by L, and when the far end is hinged, it is 3I by 4L. Next is our distribution factor. Distribution factor is the stiffness of the member divided by the stiffness of the joint, right? So what do we mean by distribution factor is, suppose we have a joint like this and we have applied a moment M like this, right? So every member, how much moment they will going to have. If we need to decide that, we will going to use the distribution factor. This entire moment M applied over the joint will be distributed in different members with respect to their distribution factor. This distribution factor is calculated. This distribution factor is calculated as stiffness of the joint, stiffness of the member divided by the stiffness of the joint, So for example, if I need to calculate the distribution factor for member OA, it simply means I need to take the stiffness of member OA divided by the total stiffness of the joint. As we have seen that the stiffness of the member OA, is 4 EI by L and the total stiffness is 7 EI by L. So distribution factor for member OA is 4 EI by L divided by 7 EI by L. So here the distribution factor for OA comes out to be 4 by 7. Similarly, the distribution factor for member OB is equals to stiffness of member OB divided by stiffness of joint O. So stiffness of member OB is 3 EI by L divided by stiffness of joint O, which is 7 EI by L. Which comes out to be 3 by 7, right? If I talk about this distribution factor for member OC, distribution factor for member OC, it is equals to stiffness of member OC divided by stiffness of joint O. So stiffness of member OC is 0, hence your distribution factors is 0, right? So whenever moment M is applied over any joint, this moment M will be distributed in different members with respect to their distribution factors. So these distribution factors are used to give us the value of the moment m which is applied over the joint, how it will be distributed over different members. So if the distribution factor for member OA is 4/7, it means that for this OA member, out of this m, the 4/7 of this m will be acting for this member OA. 4/7m will be acting over this member OA. Similarly, for this member OB, 3/7m will be acting over this member OB, and no moment will be acting over this member OC. When you add this 4/7 and 3/7, you will get the total moment as m. So distribution factor is basically used to distribute the moment, to calculate how the moment at a joint will be distributed among its different members. Correct? Okay, chalo. So distribution factor is the stiffness of the member divided by the stiffness of the joint. Carryover moment, when far end is fixed, when your far end is fixed. For suppose you have a member like this, when your far end is fixed, you have applied a moment m like this, then the part of this moment will be carry forward to the other end. And when your far end is fixed, the carryover moment will be m/2. The carryover moment will be equal to m/2. When some part of the moment is transferred to the other point or the far end, then that is known as the carryover moment. Whenever your far end is fixed, half of the moment that you have applied at the near end will be transferred to your far end. When your far end is hinged, there will be no carryover moment, and when your far end applied is free of the end of the cantilever, when moment is applied at the free end of the cantilever, the carryover moment is minus m, right? The carryover moment is minus m. This is not the cantilever beam. Right? This is my near end, and if I apply moment at the near end, half of the moment is transferred to the far end, right? If I apply the moment or carryover moment, at the free end of the cantilever, the carryover moment will be equal to minus m, right? Next is the carryover factor. Carryover factor is simply the carryover moment divided by the applied moment. So for my far end fixed, my carryover factor is 1/2. For far end hinged, the carryover factor is 0, and for cantilever beam it is minus m. As the carryover moment for cantilever beam is minus m, therefore the carryover factor will be -1 for the cantilever beam. So here we have a question. Just deal with this question. I am just coming in a minute. Deal with this question. Okay. So coming back to the question says that calculate the distribution factor for the member AB and AD of a box section shown in the given figure. So this is the figure given to you where you need to calculate the distribution factor for AB and AD, right? Whenever any rigid joint is there, you need to consider that as a fixed end, right? Whenever any rigid joint is there, consider it as a fixed joint. We know that if I consider this AB and AD, this is my AB and AD. So this is A, this is B, and this is D, right? In order to calculate the distribution factor, I need to know the stiffness of the members and I need to know the stiffness of the joint. If I know these two things, I can very easily calculate the distribution factor. So, for this member AB, since this end B is a rigid joint, hence we consider this as a fixed, right? We consider this as a fixed end. So, stiffness for member AB is equals to 4EI by L of AB. 4EI of AB and L of AB, right? Since EI is constant, but length of the member AB is 2.5. Length of the member AB is 2.5. So this is 4EI by 2.5. Similarly, KAD is again, this is a rigid joint, hence this is taken as a fixed support only. So for a fixed end, the stiffness is 4EI by L of AD. 4EI by L of AD, that is equal to 4EI by 5. 4EI by 5, right? You can add these two to get the stiffness of the joint. So stiffness of the joint A will be equal to the stiffness of the member AB plus the stiffness of the member AD. Stiffness of the member AB is 4EI by 2.5 and stiffness of the member AD is 4EI by 5. So when you add these two, you will get as, this is 8, 12EI by 5. This will be 12EI by 5. So this is the stiffness of joint A. If I talk about the distribution factor for AB, it will be equal to stiffness of member AB divided by the stiffness of joint A. So stiffness of the member AB is equals to 4EI by 2.5, divided by the stiffness of joint A, that is 12EI by 5. This is 12EI by 5. So this is 1, this is 2 times. So this is 2 times. This is 1, this is 3 times. So 2 by 3 is the distribution factor for member AB. 2 by 3 is the distribution factor for member AB. For member AD, distribution factor for member AD, is equals to stiffness of member AD divided by the stiffness of the joint A. So this is 4EI by 5 divided by stiffness of the joint A. This is 12EI by 5. So this comes out to be 1 by 3. One more thing, just note it as a point, mark it as an important note point. The summation of sum of distribution factors at a joint, sum of distribution factors at a joint of all the members is equal to 1. Is equal to 1. The sum of distribution factors for all the members is equal to 1. LAD is 2.5. No, it is 5. LAD is 5. This is not 2.5, this is 5 meters. This is 5 meters. It is 5 meters. If it has been 2.5, then the distribution factor should be equal for both the members, right? So, this is how you deal with the question of distribution factors. Next, we have for the frame shown below, the distribution factor for the member BC and BA at a joint B is. You need to calculate the distribution factor for the member BC and member BA for joint B, right? Just quickly do it. So distribution factor के लिए सबसे पहले we need to calculate the stiffness of member BA. Stiffness of member BA, since far end is fixed, so this is 4 EI by L, and length of the member is 6 meters. The length of the members is 6 meters. Similarly, KBC is equal to, since this is a rigid joint, hence considered as a fixed end, right? So this is also 4 EI. Now take care, this EI is 2 EI. This EI is 2 EI. So in place of EI, you have to substitute 2 EI. So this is 4 into 2 EI divided by length of the member. The length of the member is 8 meters. The length of the members is 8 meters. So this is 4 2s are 8. 8 and 8 are going to cancel out, and this will be EI, right? So the total stiffness of joint B is equal to stiffness of member BA plus stiffness of member BC. When you add these two, you will get 4 by 6 plus 1. So this will be 10 by 6 EI. It will be 10 by 6 EI is the stiffness of joint B. This will be the stiffness of joint B. You got the stiffness of joint B. So stiffness of joint B is 10 EI by 6. Then you have the stiffness of member AB. Stiffness of member BA, this is equal to 4 EI by 6. The member BA, it is 4 EI by 6, and the stiffness of the member BC, it is EI. Stiffness of the member BC, it is equal to EI, right? So using these three terms, we can calculate the stiffness for distribution factor for BA. It is the stiffness of BA, that is 4 EI by 6. 4 EI by 6 divided by the total stiffness of the joint, that is 10 EI by 6. This is 10 EI by 6. So this comes out to be 2 by 5. This comes out to be 2 by 5, right? Similarly, distribution factor for BC is equals to the stiffness of BC, that is EI, divided by the total stiffness, that is 10 EI by 6. So this comes out to be 3 by 5. As you can add these two, you will find that distribution factor for BA plus distribution factor for BC plus distribution factor for BC is equals to 2 by 3, 2 by 5 plus 3 by 5. So this comes out to be 1. So when you add the distribution factors for the individual members at a joint, that sum of the distribution factor comes out to be 1. Okay. Chalo, moving on with this. Okay, we have one more question which says that if all the members of the frame shown have the same flexural rigidity, means EI is same for all the members and the length is L, right? If a moment M is applied at joint B, the rotation of joint B is, right? For calculating the rotation, if you know the stiffness of the joint B, right? So this rotation theta of joint O, sorry, the stiffness, rotation theta of joint B is nothing but the stiffness of joint B multiplied by, so this rotation B is equals to moment applied at joint B divided by the stiffness of the joint B. Divided by the stiffness of the joint B will going to give you the rotation of joint B, right? Now it is very easy for calculating this KB value, We will going to calculate very easily, right? For this member AB, the far end is fixed, right? The far end is fixed. So stiffness for AB, I can write here directly. Stiffness for AB is 4 EI by L. It is 4 EI by L. Similarly, for this member BD, again my far end is fixed. Hence, the stiffness is again KBD is 4 EI by L. It is again 4 EI by L. For this member BC, since my far end is hinged, so the stiffness of the member BC is 3 EI by L. Stiffness of the member BC is 3 EI by L. Stiffness of the member BC is 3 EI by L. Getting this or not? Please tell me yes or no. Are you getting this? Are you getting this or not? Okay. So stiffness of this joint B is the sum of the individual stiffnesses. So stiffness of joint B is equals to the stiffness of member BA plus stiffness of member BD plus stiffness of member BC. So this is 4 EI by L plus 4 EI by L plus 3 EI by L plus 3 EI by L. So this is 4 plus 4, 8 plus 3, 11. So this comes out to be, so stiffness of joint B comes out to be 11 EI by L. It comes out to be 11 EI by L. It comes out to be 11 EI by L. It comes out to be 11 EI by L. We know the stiffness of the joint. Once we know the stiffness of the joint, we can calculate the distribution factor. So the distribution, once we have the stiffness of the joint, then the rotation of this joint B, this rotation of the joint B is M upon stiffness of the joint B. So this M upon stiffness of the joint B is 11 EI by L. It is 11 EI divided by L. So it comes out to be ML upon 11 EI. It comes out to be ML upon 11 EI. So this is the rotation of my joint B. This is the rotation of joint B. This is theta B. This is my rotation of joint B, that is ML upon 11 EI. Correct? Are you getting this? Getting this or not? Please tell me yes or no. Are you getting this or not? Please tell me yes or no. Have you got this question? Shall we move forward? Shall we move forward? Okay, chalo. Nice. In the next question, what is the value of theta B for the frame shown, right? You are given with the frame and you need to calculate the value of theta B. Now understand this. This theta B will only going to happen at a joint when some moment is applied over the joint, correct? This theta B will never going to happen due to any point load. It will only going to happen when there is some rotation at a joint, right? So just resolve this figure, Consider this as the extended arm 2 into 10. So this is 20 kilonewton meter of the moment applied at joint B. So this figure can be resolved as like, so this is my BC and this is my BA. So this is and this is my, so this is my B, C, and this is A. This extended arm will going to provide a moment of 20 kilonewton meter. 10 into 2 will going to provide a moment of 20 kilonewton meter over this joint, and due to this moment of 20 kilonewton meter, the rotation of this joint will going to happen. The rotation of this joint B will going to happen. So this is 20 kilonewton meter, and due to this 20 kilonewton meter, the rotation of this joint B will going to happen. In order to calculate the rotation of this joint B, theta B, you have to get the stiffness of joint B. In order to get the stiffness of the joint B, you need to get the stiffness of the individual member. So we can quickly calculate the stiffness of these members. So since EI and length is same for both the members, so I can write it as KBC is equals to KBA is equals to 4 EI by 6. It is equal to 4 EI by 6. Okay, so the total stiffness of the joint B is equals to, adding it twice, that will give us 8 EI by 6. It will be 8 EI by 6. Since KBC plus and KBA are same, so 4 EI by 6 plus 4 EI by 6, it is equals to 8 EI by 6. So this, now this is the stiffness of joint B. This can be further reduced to, it can be written as 4 EI by 3. It can be written as 4 EI by 3. So this is my stiffness of the joint. Once I have the stiffness of the joint, the rotation theta B is nothing but the moment divided by the stiffness of joint B. So this rotation theta B is equals to m upon 4 EI by 3. M upon 4 EI by 3. 4 EI by 3. So this comes out to be 3m upon 4 EI. This is the rotation of joint B. This is 3m upon 4 EI. This is the 3m upon 4 EI. So using this, you can calculate the rotation of any joint, correct? Then find the bending moment of all the members connected to joint O. Again, this is a question where you have to find the distribution factor, and using this distribution factor, you can calculate the amount of moment which has been distributed to different members, correct? Using this distribution factor, we can calculate the amount of moment that has been distributed to different members. In order to calculate the distribution factor, calculate the stiffness of members. So stiffness, here you have a diagram in which EI and L is same for all the members. EI and L is same for all the members. So for member OA, since far end is hinged, KOA is equals to 3 EI by L. It is 3 EI by L. Similarly, KOB, since far end is free, the stiffness of this member will be 0. So KOB is 0. Then for KOC, since the far end is fixed, hence the stiffness of KOC is 4 EI by L. KOC is 4 EI by L. 4 EI by L, right? So this is the stiffness of different members acting at this joint. Now, adding all these stiffness, you will get the stiffness of joint O, that is stiffness of OA plus stiffness of OB plus stiffness of OC. This gives us 3 EI by L plus 4 EI by L. This gives us as 7 EI by L. 7 EI by L, right? 7 EI by L. We have the stiffness of the joint, we have the individual stiffnesses. So the distribution factor for member OA is the stiffness of the member OA divided by the total stiffness of the joint. Stiffness of the member OA is 3I by L and the total stiffness is 7EI by L. When you divide these two, you will get the distribution factor as 3 by 7. Right? Similarly, distribution factor for member OB is equals to stiffness of member OB divided by the total stiffness of the joint. Since the stiffness of member OB is 0, hence the distribution factor for OB is 0. Next, distribution factor for OC is equals to stiffness of OC divided by the total stiffness of the joint. So, stiffness of OC is 4EI by L and the total stiffness of the joint is 7EI by L. So, distribution factor comes out to be 4 by 7. Okay. So, when your distribution factor for OC is 4 by 7. So, when you apply a total moment M, this moment M will be distributed with respect to the distribution factor. This total moment M will be distributed. For this member OA, the distribution factor is 3 by 7. Hence, the amount of moment coming to this member OA will be equal to 3 by 7 M. Since the distribution factor for this member OB is 0, hence the amount of moment coming to this member OB is 0. The distribution factor for this OC member is 4 by 7, hence the moment coming to this member OC is 4 by 7m. Okay, so out of the total moment applied at the joint, it is distributed in such a fashion. At this particular joint, when you apply the total moment, 3 by 7m will be taken to by OA, 4 by 7 will be taken by OC and none will be taken by OB. Okay, so this is how you need to deal when the questions are asked regarding the distribution factor. Next. Then find the bending moment at the fixed support of the beam shown in the figure. Okay, just attempt this question. Please attempt this question. Please attempt this question. Okay, so for this question, you need to find the bending moment at the fixed support. So this is my fixed support where you need to find the bending moment, right? So in order to deal this type of question, this beam can be resolved as like this. So this beam can be resolved like this. So here we have a beam like this, whose this distance is B, and you have a support like this. This is our support. Over this support, a moment of P into A is acting. A moment of P into A is acting. Now, my dear students, when a moment of P into A is acting, the part of this moment will be transferred to the far end, right? So, when our far end is fixed, the moment that is transferred, is equal to PA by 2. If M is the moment that is acting at our near end, so this is our near end, then half of the moment will be transferred to our far end, which will be equal to M by 2. So the moment at the fixed end is equals to PA by 2. Okay, so this is an easy question. Moving on with this. Find the carryover factor. For this beam. Try this question. Please try this question. Quickly try this question. Okay. So carryover factor is carryover moment divided by the applied moment. Carryover moment is carryover factor is carryover moment divided by the applied moment. You need to find the carryover factor, right? Carryover factor. When you apply moment at this end, so this is our near end. This is our near end. Some part of this moment will be transferred to our far end. So this is our far end, right? Some part of the moment will be transferred to our far end. So amount of moment that is transferred to the far end is termed as the carryover moment, and the amount of moment applied is given as m. It is given as m. So you need to find this carryover moment in order to get the carryover factor. Just take this side, just take this side of the beam, take this side of the beam, just take this side of the beam and draw the free body diagram. So here we have a hinge support, then we have a hinge here, and over here we have applied one moment m. In order to balance this moment m, a reaction of opposite direction. This is the clockwise moment. So the opposite couple has to develop, the opposite couple has to develop in this part of the section, so that this section should remain under equilibrium, and that is equal to, the reaction force will be equal to m by L. This is also m by L, right? So when m by L force is acting over this portion, when you consider the FBD of the other part, so if m by L is acting upwards in the left side, in order to keep that balance, we need to apply m by L in the downward direction like this. In order to balance this m by L at the support, there will be upward reaction like this, and this value is again equal to m by L. This m by L forms a anti-clockwise couple. It forms a anti-clockwise couple, due to which a reaction moment will going to develop, the value of which will be equal to m at the fixed end. So at the fixed end, the moment developed will be m in the clockwise direction. So here, from this applied moment m, the carryover moment is also m, and the direction is also clockwise, right? So when we talk about the carryover factor, the carryover moment here is the carryover moment. So for carryover factor, the carryover moment is m, and it is also in clockwise direction, hence positive, and the applied moment is also in clockwise direction, hence its value is also positive, right? So the carryover factor comes out to be 1 for this fixed end, right? For this fixed end. Is this clear to everyone? Okay, chalo, moving on. Next we have the slope deflection equations, right? So using these two equations, we can simply calculate the different moments that are present in any members. You can simply use these two equations to calculate the different moments that are present in our members, right? To calculate the different moments that are present in our members. Usually, very less questions are framed from slope deflection equations, because from slope deflection equations, usually you need to solve two simultaneous equations, which takes a lot of time. So from slope deflection equation, you can expect less number of questions, right? Moving on with this, just take a snap of this question and you can try. It is a very easy question of slope deflection equation, and using these equations, you can clearly solve this, right? Okay, chalo. Talking about IMS GATE Academy, my dear students, if you just log into imsindia.com, you will get a web page like this. And after getting this web page, if you go into GATE ME, you will going to have access to our program that we IMS GATE Academy provide. We basically provide three types of program. We provide classroom program, hybrid classroom program, exclusively live online program, and then we have a self-learning program. In our classroom program, we provide 750 hours of offline teaching. Along with it, in order to practice, we provide you with theory books and exercise books containing 4000 plus practice questions which are well versed in level 1, level 2 and level 3. Then we provide you with GATE previous year question book. We have a very good doubt solving portal. Along with it, we provide my plan strategies, and we provide a test series where we provide 130 plus tests, in which we provide a chapter test, subject test, multiple subject test, full length test, and then we have a post GATE guidance interview program, right? Next is the hybrid program, where 750 hours of classroom teaching is done, where 2/3 of the teaching is provided in the offline mode and 1/3 of the teaching is provided in the online mode. Rest all the facilities that are provided in the classroom program are provided in our hybrid classroom program as well. Next, we have exclusively live online program, where we provide 750 hours of live teaching along with all the products that we provide for the classroom program. Last, we have the self-learning program, where we provide the recorded video lectures of more than 400 hours, and along with it, we provide the facilities that are provided in our classroom program. We talk about, at IMS GATE Academy, we believe in the methodology of LPT. For learning, we have a very crisp and precise and detailed theory as well as the classroom program that you can enroll and avail all the facilities that we provide, right? For learning, we have the expert faculties, we have a comprehensive coverage of the subjects, and we have a dedicated theory books which contains solved problems. For practice, we have a exercise book in which we have level 1, level 2 and level 3 versed question, from which you can even identify how much you are actually prepared and what are the areas which actually require extra attention. Then we have a test in test series, where we provide more than 130 plus tests, right? So here are the details of our test series. You can just take a snapshot. According to the number of tests and the number of questions, we have provided different durations of the test, and accordingly we have provided the marks for these tests, right? Next, we have the GATE at Zero Fee program, where at zero cost you can have the 100 plus hours of concept video, 12 chapter tests, 6 subject tests and 6 past GATE papers free of cost. These are not at all chargeable. Next is, this is our student portal, where all the lectures are well placed, and in this student portal you have this doubt solving portal as well, where you can just click and post your doubt either by, this is our doubt portal where you can post your doubt either by writing your doubt, or you can just take a snap of your doubt and paste it, and you can just post it doubt, and this doubt has to be cleared within 24 hours, my dear students. Next is, we have this very exclusive facility at IMS GATE Academy. We provide one-to-one guidance to our students. Those are known as one-to-one My Plan sessions. Also, we provide one-to-many sessions for a group of students. These My Plan sessions helps our student to remain focused and be specific about what they are reading. They can even discuss their preparation strategy and revision strategy, or all the doubts that they are facing during their preparation of GATE, right? So these are the exclusive facilities that are provided at IMS GATE Academy. My dear students, my aim for taking the sessions of environment and structure is to give you the basic idea how the questions can be framed. In the last, before this session, I would like to tell you one thing. GATE is an aptitude examination based on your technical knowledge. Try not to mug everything and anything that is coming to your desk. Read precisely, but read for multiple number of times, right? Read for more number of times. Revise your content more. Practice your content more. Practice more number of questions, because in your GATE examination, the thing which are asked is the question, and these questions can only be solved easily if you have practiced them well using our test series and our exercise book. Okay, so all the best from my side. Do well in your GATE examination and in your life. And my dear student, GATE is just an examination, and you can crack in just a snap if you have really good dedication and consistency in your preparation. So I, Prateek Mishra, signing off for this session, and all the best to you. Thank you for listening patiently. Thank you so much.